Dear students, welcome to the second lesson of Introduction to Financial Mathematics. And today we are going to start with the book. We will start with chapter 1. In chapter 1, there's a lot of measure theory. And we will go a little bit faster through chapter 1. So if you are not familiar with measure theory yet, then please study chapter 1 of this book rigorously. Again, some of the information has already been taught in the course measure theory, and some of the information in chapter 1 is known from earlier courses on stochastics. We start with a recap of the problem setting from last time. Last time we discussed that we are dealing with a stock price ST at time t, and that is a random variable. And the collection of stock prices ST for t larger or equal to 0, that is called the stochastic process. And for that, we will work with the rules for stochastic processes. And some of these are being taught in this course. In practice, one does not only trade in stocks because stocks are considered risky. Stocks can go up and down, but also in other financial derivatives. For example, in pension funds, there's a lot of interest rate related products like bonds, in Dutch obligaties. But there are also other products that are being traded, other interest rate products, but also other products like futures that have other payoffs, and also options. Last time we discussed that a combination of stocks and certain options in a portfolio basically makes a portfolio more safe, because the option can be used to hedge the stock. Let's concentrate on options. And what we saw last time is the European call option. We have defined the contract. It was a contract that gives the buyer, the holder of the option, the right, but not the obligation to buy certain stock at a certain prescribed time in the future, capital T, which we call the maturity or the expiration date. And we can buy that stock for a fixed, also predefined amount, K. And that we call the strike price or exercise price. And that buying of the stock is an option, not an obligation, and it is regardless of what the stock price is at time t. The other party of the contract, the writer or the seller of the option, has the obligation to deliver the stock when the holder decides to exercise the option. Now, the payoff of the European call option at time capital T is the maximum of ST minus K and 0. And we sometimes denote that, or we often denote that, with the argument in brackets and a plus sign, a superscript plus sign there. That stands for the maximum of the argument and 0. So it is ST minus K when ST minus K is larger or equal to 0, and it's 0 otherwise. Because then when the stock price is less than the strike price, then the option is not exercised. So it terminates without any value, Now, an important question is, we know what the option's value is at final time. What is the price or the value of the option contract at time 0, at initial time? So what would be a fair price for the option to sell by the writer to the holder? So what is the fair price of the option? And to answer such a question, we essentially need to quantify two things, being, first of all, what is fair? And what means fair price? And here is the notion of martingales and risk-neutral measure that we will discuss in this course. And the second thing to learn is how to model the price process S sub t for t larger or equal to 0. And for that, we need the notions of Brownian motion and Ito calculus. And we abbreviate those by BM and IC, as you see here. By BM and IC, they are measure theoretically based. And however, only basic notions of measure theory will be needed in this course. We start with the general probability spaces, which are measure theoretically based. And usually our probability space, when we do an experiment, then the set of all possible outcomes, which we denote in probability theory by big omega, the set of all possible outcomes is usually uncountable. And the collection of sets or events that can be measured and even on which we are able to assign a probability measure should be closed under certain set operations. Because if A occurs and B, then we expect the linear to occur and the intersection and the complements, etc. So the set of all possible events, the sets, should be closed under certain set operations. And this leads us to the notion of sigma algebra. So let's define that. Let omega be a set. The collection script F of subsets of omega is called the sigma algebra if three things hold. First of all, the empty set should be in F. Secondly, if A is in F, then a complement should also be in F. And thirdly, if A sub I, a countable sequence, is in F, then the union of A sub i's should also be in F. So if each I is a possible event, then also the union is a possible event. Let's write a remark about this. Well, a remark is that 1 and 2 imply that omega is in F. And how can we see that? We can see that rather easily. Omega is, of course, the empty set complement. Well, by 1, we have that the empty set is in F. By 2, we have that the complement of this event is in F, and the complement of the empty set is omega, and therefore omega should also be in F. Yes. And then we see, we can also show easily that 2 and 3 imply that when a countable sequence is in F, then the union of countable sequences should also be in F. And how can we see that from 2 and 3? Well, first of all, that union is the union of all I can be written as the complement of a complement. So it is the union. So the intersection of A sub I is the union of A sub I complement, and from that the complement. Yeah, that is an equivalent writing. Well, A sub I is in F, then the complement should also be in F. That is what 2 tells us, right? So this part is in F. Then 3 tells us that the union of these events should be in F. And then 2 again tells us that the complement of that bigger event should again be in F. And that is the intersection of all A sub i's. Yeah, so indeed, it's closed under countable unions as well. So now we have formalized the definition of a sigma algebra. This is the collection of events that we are able to define a probability measure on. Let's define what we mean by probability measure. So a probability measure, P, on F is a function from the sigma algebra to 0, 1, satisfying 2 conditions. First of all, P omega, omega which is a member of F, P omega is equal to 1. That is the sure event. And secondly, and the second property is called sigma additivity. If you have a countable collection in F being pairwise disjoint, then the probability of the disjoint union, where the dot inside the union symbol denotes the disjoint union, the disjointness. So the dot emphasizing that it is disjoint. And that probability is the sum of the individual measures. This property is called P is sigma additive. All right, with this now we have a set, omega. We have a script, we have a sigma algebra F, and we have a measure, and we call the triplet omega FP a probability space. And only in the discrete space, in the discrete case, P can be defined on points because it's countable. Yeah, and from probability theory in the first year, you know that P can be defined on points in the discrete case. The discrete space consists of finitely many possibilities, or at least countably many. And in this case, it makes sense to talk about the probability of an outcome. Otherwise, in the general case of an uncountably probability space, people talk about the probability of an event rather than the probability of an outcome. Because in most cases, the probability of a single outcome is equal to 0. You have seen that, for example, in the continuous distributions. So let's look at two important examples that we will be seeing more often in the course. Here, I'm going to be rather quick. The first one is what you used to know as the uniform, but we will look at it a little differently. We will relate it to the uniform distribution. So here the underlying space, so here the underlying space is usually an interval, which we take as 0, 1 here for simplicity. It's like picking a point at random, and let's take as the sigma algebra, the Borel sigma algebra, and I'll explain what this is. And we take as the probability P, what we call the Lebesgue measure. Also explain that in a second. And the Lebesgue measure in the book is denoted by calligraphed L. Let me tell you what it is. B on 0, 1, the Borel sigma algebra on the unit interval, is the smallest sigma algebra containing all relevant intervals. And the probability Lebesgue measure is just on intervals. When you measure it on intervals, and these intervals can be open, closed, semi-open on either side, it is just the length of the interval because we know that the length of a point is equal to 0. So the probability here can also be the probability of an open interval or semi-open interval, etc. So that is B minus A, yeah? And for arbitrary Borel sets, this is not as easy, but there's a way to get it. But in most practical cases, it is sufficient to consider intervals. So we stop here with the intervals. And when we say that a random variable x defined on omega equal to 0, 1 has uniform distribution, remember, we write x omega is equal to omega, the identity. It has uniform distribution if P of the set of all omega in 0, 1, the probability of the set of all omega in 0, 1, such that x omega is in AB is equal to omega, is x. It's just the length of the interval. Another important example for us is the so-called product measure. Let's consider the space omega, in which I denote by 0 and 1 to the power n. These are infinite sequences. So you can think of it as the space of all infinite tosses of a coin, where 1 is seeing a head and 0 is seeing a tail. The space of all infinite coin tosses, and here script F is going to be the smallest sigma algebra generated by what we call cylinders, or containing all cylinders. And cylinders are the sets where you specify finitely many coordinates like this. Yeah, these are called cylinders, and they're telling you what happened in the first n tosses. Yeah, so omega is in set omega, where with omega 1, a being equal to a sub I1, etc. Omega n being able to a sub In, and these a ij's are either 0 or 1. And so these are called cylinders, and they tell you what happened in the first n tosses. I'm going to take the product measure. Yeah, I'm going to take the product measure. It gives the probability of a head, or the probability of a 1, that's a coding, and it comes with a small p, as you see it here. Suppose every time I see a head, it's equal to small p, and seeing a tail, or a 0, comes with probability 1 minus p. Now, once you specified what happened for each toss on cylinders, it's enough to define p on cylinders. So, on cylinders, I just write the probability that I specify, say, a sub 1 until a sub In, as follows. The probability omega in the set omega I is equal to a sub I1 to omega n equal to a sub In. That is then p to the power a sub I1 plus etc. a sub In times 1 minus p to the power n minus that number a sub I1 plus etc. a sub In. So if you think about it a little bit, then you see that sum a sub I1 to a sub In, that represents the number of ones, or the number of heads. So we do little p to the power of the number of heads, and 1 minus p to the power number of tails, Bernoulli experiment. And why is it enough to specify or measure on subsets? Because these sets have a construction which we call a semi-ring. And there's a theorem, Karateadori's extension theorem, that says that once you know it on cylinders, then there's a unique way to extend it to the whole sigma algebra. But again, for applications, it's sufficient to stay on cylinders. Yeah, and this is called the product P1 minus P measure. Yeah. Usually when we have a theorem involving measures of sets, it's enough to check it on these generators. So for practical purposes, it's enough to check it on cylinders. Well, we have some terminology here. If omega fp is our probability space, and A in F, set A in F has the full measure, and so it has probability 1, then we say that A is a sure event, or A occurs almost surely, and we denote that by A dot S dot. Shorthand notation. So now let's move on to random variables. You have seen them in a simplistic form, but now we're going to be more rigorous. And of course, for the random variable, you still remember that there is a distribution attached, but now we do it a little bit more rigorous. So we have our probability space, omega fp, the underlying thing, and a random variable, which is denoted by x, often in probability theory. That is a function from omega to r. That is measurable function. That means that for any Borel set B in the Borel sigma algebra, so here for any Borel set B in the Borel sigma algebra, the smallest algebra containing all the intervals, in fact, the B can be taken to be an interval, for any Borel set, if you look backwards, it is, if you look at x inverse b, if you look at x inverse b, it is the inverse image, which is everything in omega, that gets mapped under x to b. And usually in probability theory, people drop the argument, so they simply write x in b. But what we mean is, of course, what is here. Omega in omega, x omega in b. And that is then in F, that lies in F. So in other words, the inverse image of a measurable set in R is a measurable set in X. And as I mentioned, to check measurability, it's enough to consider B to be an interval. It can be closed, open, half infinite, etc. Now with the random variable, we associate a measure. Yeah? For us, a random variable and a measure are analogous objects. Let me elaborate a little bit. That is what we call the distribution measure of the distribution measure mu x on R BR of a random variable, and this is very important. We write it like this. Let x be a random variable. We find on omega fp with x together with the original p, we associate the measure on R on the reals with the Borel sigma algebra as follows. Mu sub x, we give it a subscript to denote the variable x on the interval AB. Yeah. This is how I define this measure on elements of B R. So it's enough to look at intervals, and the measure gets this subscript x to emphasize that it's a new measure on RBR associated with a random variable x. And we define it in this form. Yeah. By definition, if we take the interval AB and we pull it back via x so that it is a set that lies in F, because x is measurable. And because it lies in F, we can apply the probability P defined on F. And to be more elaborate, this is exactly the probability, the set of all omegas, such that x of omega lies in AB. And as I said, in probability theory, one often drops the argument. So we end up again with this notation. And we denote the last set by P, and the set of all x that lie in AB is also sometimes written like this. And mu x is called the distribution measure of x. Let's make a picture. So we have an abstract space, omega. This is our abstract space, and the random variable, the measurable function, x. We see x. X is taking values in R. It's taking values in R. And I define, yeah. And on omega, we have a measure P. Yeah. And this measure P gets pulled back. It gets pulled back. The arrow is going forward, but it means it gets pulled back to mu x. So mu x is actually P dot x inverse. Yeah. So let's move on with a remark. Yeah, the distribution measure is not uniquely defined via a random variable. Different random variables can have the same distribution measure f. Let's show that with a small example. Take xy defined on 0, 1 with the Borel sigma algebra, and p, the Lebesgue measure, is a length. And I define x by the identity map. Yeah, so here you see x is defined by the identity map. And y is the flipped thing, 1 minus omega. Yeah, it's 1 minus x omega. Of course, from the definition, we see that x is not equal to y. But when we look at the corresponding distribution measures, which I only have to check with intervals, I put everything together now. So x is not equal to y, as I said. But if we look at the distribution measure, mu x on AB, it is defined as follows, as written here. So the probability omega in 0, 1, x omega is equal to omega is in AB, is the probability of AB, and it's the length is B minus A. And if we look for y, which is 1 minus x, it's the probability with omega in 0, 1, such that y omega is 1 minus omega is in AB. That is the probability of the interval 1 minus B, 1 minus A. And again, if we look at the length, it is 1 minus A minus 1 minus B. And that is B minus A, and that is equal to the distribution measure of x. So mu x is equal to mu y. Yeah, if two measures agree on the generators, on the intervals, then they agree on all elements of the sigma algebra. So from here, we can conclude that these distribution measures are in fact the same. Let's go to the distribution measure function, the distribution function, which you have already seen. Here we are in the distribution measure a little bit more advanced, as we are defining a new measure. And in distribution, it's looking at this measure on a specific set. Yeah, let's define a distribution function of a random variable x, defined on omega p. It's a function, usually denoted by cap f to, by capital F, to emphasize that it is associated with x. It has a subscript x. It is a function from the reals to 0, 1. Yeah, fx is from the reals to 0, 1. And it is defined as follows. Fx is the probability that capital X is less or equal to small little x. And the definition is as follows. The probability that omega and omega is such that x omega is less or equal to x. And that is, in fact, if we look at it carefully, this is the distribution measure mu sub x on the interval minus omega to x. Yeah, and this is, of course, written in extended forms with the omegas, and we call the definition of mu x. So you see that this is indeed mu x on the interval minus infinity to x. So the distribution function is defined via the distribution measure. If one gives formulas for mu x, we don't have to refer to p. If x is a continuous random variable with a density f, then this means that f is non-negative with a total integral 1. Then, in fact, the distribution measure of x is just the integral over AB of fx dx, or written as follows. The reference to p then disappears. So if the density is given right away, we don't have to refer to P anymore. Another example we have seen in probability theory 1, when we say that X is discrete, a discrete random variable with values x1, x2, etc., finite or countably many, then mu X is defined and has atoms. Yeah, I can look at a single atom which lies in R, and little xi, what we call pi, so the probability that X is equal to xi, in the discrete case this is possible, that is a little pi, and in general, mu X of the set of all omega, for which X lies in a certain set P, is just the sum as you see it here. Right? So now we have a notion of a random variable, of a distribution measure, and a distribution function. We go to the expectation of a random variable, yeah, which is an average value. Yeah, we have seen in probability theory 1 again that when X is discrete with values x1, x2, etc., then we have defined the expectation of X to be simply the sum of little xi times the probability that X is equal to little xi, right? As we write it here. Yeah, so then each value is weighted with the probability of seeing that value. When X is continuous with a density F, then the expectation of X is the same. It is the same ID, but the sum is replaced by an integral. And this should, of course, exist. It should have a finite value, but E of X is then the integral from minus infinity to infinity x fx dx. Now we can ask ourselves, what if X is neither discrete nor continuous? In the elementary stage, it is continuous or discrete, but it can also be neither discrete nor continuous, a combination of both. And the question is, how can we define the expectation of X then? And for this, we need the notion of the Lebesgue integral, which is a generalization of the Riemann integral. Yeah. One difference between these integrals is that in the Riemann integral, usually the function f has a domain, a closed interval, and f is continuous or smooth enough. It doesn't go crazy then. You define the Riemann integral as a partition of AB, and then on each little interval, you take the value at some point, you look at the Riemann sums, and you refine, you take limits, you can get the value of the Riemann integral, right? That is how it is well known, typically. Now, in the general case, when we are looking at random variables, our domain need not be a closed interval. And in fact, it can be an abstract space, which we call omega. It's not an interval. So what we have is an X going from some abstract space to R. Yeah, is omega. Going from some abstract space to R. And the question is, how do we partition our omega? Yeah. To do that, in principle, we partition, well, we have an omega here, we have an X. Again, we have an X. Yeah. We have R. This is a straight line, this is R. Yeah. And we can partition R into small intervals. Give them a little size. Yeah. Tiny little intervals. And we have to do this repeatedly, of course. And taking this partition, we pull each interval here back to X and find out the set of all points that get mapped onto this interval. Let me use red here. and I get this little interval AB, A to B, and then this gets mapped onto, for example, onto this part of the omega space. So we have here X inverse AB. Yeah. So we look at X inverse, the inverse of AB, and we look at all points that get mapped on AB, and we do it for every such interval. And this way we get a partition of X into sets, and on each set we know that the X value is in a certain range between A and B. We take these smaller and smaller, and then we take the limits, and this way we get the Lebesgue integral. All right. So the idea of Lebesgue is that instead of partitioning your domain, you partition your range. And to get to that range, and to do it in a rigorous way, we first start, for simplicity, we start with the assumption that X is non-negative. So we do a rigorous construction of the Lebesgue integral and assume that X is non-negative. We fix it later up to, so we can always write later X as a function X plus minus X minus. Okay, we start simple first. We take an indicator function. This is simply 1 if the outcome omega is in A, and it's 0 otherwise. So it's a simple function only taking values 0 and 1. And what you do is on R, the range has 2 values. 0 and 1. And what you do, we have all of R, but we only have 2 relevant outcomes, 0 and 1. Let me draw this. This is again our omega. And here is our X. And our R again. And now we only have 0 and 1. And what we do is we pull back via X and divide our space into 2 pieces. Piece where X omega is equal to X omega is equal to 0. And a piece where X omega is equal to 1. Yeah, so we divide our space into 2 pieces, and on this piece, all our points get value 0, and here all our points get value 1. Now we use this partition. We are going to divide. It's really like a Bernoulli experiment. It's like flipping a coin with zeros and 1. You get heads when you end up in A, and tails when you end up not in A. So in this case, X is an indicator function, and then we define the expectation of X, which is equal to the integral of X dp over P, and X is the indicator function, and that is then just the probability of A. And in the next step, we take X to be a simple function of the form AI times the indicator at AI. And here what we do is if we look at this, we have our space, we have our X here. And we have these small values, A1, A2, A3, etc. And here we have the set A1, the set A2, capital A here, the set A3, etc. So this is the setting. So if we have x as the sum of over I is 1 to n AI times the indicator of capital AI, then we can define the expectation of x as the sum over I of A sub I times the probability that we are in the set capital A sub I. Yeah. And this reminds us of a discrete random variable. Yeah. Now we go for a general x and we apply the ID of the Riemann integral, but we partition in a different way. Yeah, so for x non-negative, more general, a general x non-negative, we consider for each n a partition or the partition of R of the following form. So we have a splitting of intervals, and the intervals are j over 2 to the n. We have 2 to the n intervals, and one such interval is from j divided by 2 to the n to j plus 1 divided by 2 to the n. And then j runs from 0 to n times 2 to the n minus 1. So if we have from n times 2 to the n minus 1, we end up with n from, it goes from 0 to n. And we have another piece, a big piece from n to infinity. Yeah. So this first part is from x lies between j over 2 to the n and j plus 1 over 2 to the n of 0 infinity. And we have that other part. So basically what we do is we have our R, and here we have our n, and we divide this into very many little intervals. And for this, we take the whole. But when n grows, this part gets bigger and bigger, and this part shrinks, right? Now, using the partition, we define a partition on omega by these sets A super n sub j, and that is defined as follows: omega such that x omega is in this interval, j over 2 to the n and j plus 1 over 2 to the n. And this can be simply written that I pull it back via x to get a partition of x. I'll look at x inverse of these partitioned elements for little pieces. Yeah. So x in that small partition, that very small partition here, j runs from 0 again to n times 2 to the n minus 1. And for the big piece, we consider x inverse of infinity, n to infinity. Yeah. Like this. Yeah. Then we define our x as follows: x sub n is the sum. So a subscript n is connected to it, is the sum over all these intervals. J is 0 to n times 2 to the n minus 1. And we have these indicator functions, 1 a to the 2j minus 1, and we take in the intervals the left side value. We take the left side value. Yeah, so that we do for all these sums. And then for the last part, we take n times the indicator that we are in that range, in that last part, a sub j to the power n to the 2n. And when n goes to infinity, we see that this converges to x, right? This is converging to x. So we can define now our integral x dp, the expectation of x, that is now in limit, the limit of the expectation of xn. And we can write that as the limit n to infinity of the sum j is 0 to n 2 to the power n minus 1 of that expression over here. So now we go with j to infinity. J over 2 to the n times the probability that we are in this little piece. So now we can show that this value, one can show that this value is independent of the choice of the partition on R. Now, when x is not necessarily positive, so we go one step more general, when x is not necessarily positive, we write x as we separate x plus from x minus. We write x is x plus minus x minus, and we define x plus as the maximum of x and 0, x minus as the maximum of minus x and 0, and these are both non-negative random variables. And then we can set the expectation of x being the expectation of x plus minus the expectation of x minus, provided that at least one of these expectations, x plus or x minus, is finite, and otherwise the expectation doesn't exist. So this concludes the lecture for today. Thank you for your attention and see you next time.